In this lecture, we are going to start talking about the upper bounds and the upper bound property for the real numbers, which, as it turns out, is going to be very important for the real numbers. It sort of encapsulates what's special about the real numbers, what we like about the real numbers as compared to rationals. So here is our definition. So we're going to let E be a subset of the real numbers and alpha be a real number. And then if alpha is greater than or equal to C for all C and E, then alpha is an upper bound for E. And if E has an upper bound, if there exists a real number alpha with this property, and we say that E is bounded above. So, for example, remember, let E be the natural numbers. You can think of a natural number as an integer. You can identify an integer with a rational number. You can identify a rational number with the real number. So you can think of the natural numbers as living inside R. Then this is a set that has no upper bound. So the natural numbers are not bounded above. We can define a lower bound analogously. And then, same example, the natural numbers, the set of natural numbers is a set that is bounded below. One is a lower bound. Because one is the smallest natural number. Every natural number is at least one. 0 is a lower bound. It's smaller than all the natural numbers. In this course, we're taking the natural numbers as starting at 1. That's going to be convenient for us. 1/2 is a lower bound. And so on and so forth. So notice that the natural numbers have a lower bound. They, in fact, have lots and lots of lower bounds. 1, 0, 1/2, all the negative numbers, all the numbers less than 1, and count is lower bounds. So everything less than 1 is a lower bound. Nothing bigger than 1 is a lower bound. So 1 is sort of the biggest of the lower bounds. So 1 is sort of special. 1 is sort of the natural to think of it as the lower bound. So, and it has a special name. It's called the infimum. So here is definition 1.2.2. I am, you notice, doing section 1.2 in a very different order than happens in your book. And there's both upper bounds and lower bounds. I'm going to write this definition out for the lower bound because we've seen that for the natural numbers, and leave it as an exercise to work out what you'd write down for the upper bound. Let's let E be a subset of the real numbers and alpha be a real number. And let's suppose the following things are both true. So, first thing that is true is that alpha is an upper bound for E. I think I said, lower bound for E. And the other thing that has to be true is that if beta is a lower bound, then our beta has to be less than alpha. So then we say alpha is the least upper bound, the greatest lower bound. For E, or alpha equals the infimum of E. And similar definition is the least upper bound. Also known as the supremum of E. And quick proposition, because I want to point out that I'm justified in saying the least upper bound, the greatest lower down. This is proposition 1.2.4. A set E has at most one, let's say, least upper bound. And the proof of this is pretty straightforward, and you should be able to see how to prove the same thing for the greatest lower bound. Let alpha, beta be two least upper bounds. So alpha is an upper bound. Beta is a least upper bound. So that means beta is the smallest of the upper bounds. In particular, it's smaller than alpha. So beta in particular is smaller than alpha. But the same thing's true in reverse. Alpha is the least upper bound. It's smaller than all of the upper bounds. Beta is an upper bound. So similarly, alpha is less than or equal to beta. And the only way you can have inequalities like this that go both ways is if the two things are in fact equal to each other. One other relatively quick proposition that I want to point out to you that is true, I don't believe it is in your book. Conway might have thought it was too obvious to bother writing down, but it is occasionally going to be useful, and you are allowed to use the following thing in your homework. Let's let E be a subset of F, which is a subset of R. And then if the infimum of E and the infimum of F both exist, if both of these sets have greatest lower bounds, then the infimum of F can't be any bigger than the infimum of E. That is, the infimum of F, remember, it's a number that's smaller than every element of F, so it's certainly smaller than every element of E. So the infimum of F is a lower bound for E, so it has to be less than the greatest lower bound. Similarly, if the same thing is true for the supremums, in the other order. And if all four exist, then the infimum of F less than or equal to the infimum of E less than or equal to the supremum of E less than or equal to the supremum of F. So any set that has both an infimum and a supremum, the supremum is bigger than all of the elements, the infimum is smaller than all of the elements, so the supremum obviously is bigger than the infimum. Let's go ahead and specify that none of these are empty sets, because the upper bounds and lower bounds for the empty set are just weird, so let's not go. So now I want to talk to you a little bit about whether infima and suprema, whether least upper bounds and greatest lower bounds actually exist. So it is a fact that some sets of integers or rational numbers, or R, I guess I should call these subsets of the integers, rationals, or reals, are not bounded, don't have upper bounds, so they don't have least upper bounds. You have to have an upper bound at all to have a least upper bound. But for the integers, this is the only way that this can happen. So let's so that is, if you've got a subset of the natural numbers that's not empty, then if the subset has an upper bound at all, then it has a least upper bound. And the proof of this is pretty straightforward. So we're going to let let's let A plus 2 be in E. Our set E is not empty, so it has some element, and for technical reasons, we're going to go ahead and name that element A plus 2. And let's let K be the set of all natural numbers such that A plus n is an upper bound for E. Actually, let's make it the set of all natural numbers such that A plus n is not an upper bound for E. So E has an upper bound. Let's call our upper bound A plus S, which is greater than or equal to A plus 2. So S is not in K. On the other hand, A plus 1 is less than A plus 2, so it's not greater than or equal to A plus 2. So 1 is in K. So that means, so K is a subset of the natural numbers, 1 is in K, and K is not equal to all of the natural numbers. So we're going to use the contrapositive to our induction axiom, our axiom that says you can do induction in the natural numbers. So there is a natural number, or n, such that n is in K, but the successor to n plus 1, is not in K. So that means that A plus n is not an upper bound for E. So A plus m is in E. For some, at least one m that is strictly bigger than n. And A plus n plus 1 is an upper bound. So A plus n plus 1 is greater than or equal to A plus E for all E in E, for all A plus E in E. Suppose this proof would have been a lot easier if I just said we're going to assume 2 is in our at E, but we want to be more general than that, so we're throwing in some other stuff. So in particular, A plus n plus 1, that's greater than or equal to A plus m, is strictly greater than A plus n. We can go ahead and cancel out all of the a's, and these inequalities will still be true. So A plus n plus 1 is in E. And A plus n plus 1 is greater than or equal to, as we said before, is greater than or equal to A plus E for all A plus E that are in E. And then it's pretty clear that A plus n plus 1 is the least upper bound. By assumption, and it is an upper bound, and any upper bound has to be bigger than it because it's an element of E. So therefore there can't be an upper bound that's smaller. So the integers have what's called the least upper bound property. That means that any set of integers, if it has an upper bound at all, it has a least upper bound. You can't get away from the requirement that it has to have an upper bound to have a least upper bound. For example, the set of all integers can't possibly have a least upper bound, but you do get that every set that has an upper bound has a least upper bound. And not only that, your least upper bound is also an element of the set you started with. Is a nifty fact. So another way to put the proposition we saw at the end of the last video is like this. If E is a subset of the integers and E has an upper bound, sometimes we write that as E is bounded above, then E has a supremum and a maximum. And they are equal. And we recall our definition, supremum of E is equal to alpha if alpha is bigger than every element of E, and if beta is bigger than an E for all E in E, then beta is also bigger than or equal to alpha. And the maximum is what you'd expect, max equals alpha, if alpha is bigger than E for all E in E, and also alpha is in E. So the supremum is this sort of specialized and awkwardly phrased condition, and the maximum is just the biggest element of a set. And the real numbers aren't quite this nice. So let's let E be, let's say, the open interval from 0 to 2. E has upper bounds. So 2's an upper bound, 3's an upper bound, 7's an upper bound. E has a supremum. It should be pretty clear that the supremum of E is 2. 2 is bigger than everything in E, but any number less than 2, you can find something that's bigger than it, but less than 2 that's also in E. This is a familiar property from the reals and the rationals. So 2 is not in E, so E has no maximum. So this is an example of a set that has a supremum, but it doesn't have a maximum. And those aren't too hard to come up with the real numbers, and that's just a fact we have to put up with. There are lots of sets with the supremum isn't in the set, so the set doesn't have a maximum. So let's talk about what goes on in the rationals. In the integers, you can always find a maximum and a supremum that are in particular integers. In the in the reals, well, we've got an example where you can find a set with a supremum but no maximum. Let's think about what happens in the rationals for a bit, and then we'll come back to the reals. So let's let E be our favorite set, be this set of rationals, the set of all rational numbers such that q squared is less than 2. All right, and now we went to a lot of trouble to construct the real numbers. This example is sort of trying to tell you that it was worth it, that there are some properties the real numbers have that the rationals don't, and one of them is the least upper bound property. Then E has no supremum in Q. So this is a set of rational numbers, and if all you've got in your life is the rational numbers, you don't have a supremum. In fact, this is a proposition in your book. It is proposition 1.2.9, and the proof is an exercise. So now we're going to state a theorem that tells us that the real numbers are sort of in between the rational numbers and the integers. They're not quite as nice as the integers. They're sets with no maximum, but they're nicer than the rationals. Every set has a supremum, at least every set that's bounded above. So this theorem says that if E is a set of real numbers, it's not empty, and it is bounded above, then the supremum of E exists and is in R. All right. And to prove this, we're going to have to use what we know about Dedekind cuts. We're going to have to use the fact that the real numbers are Dedekind cuts. So we're going to let alpha be the union of all the epsilons for every epsilon in E. Recall that if epsilon is an element of E, that means it's a real number. So that means it is a Dedekind cut. And that means it's a special subset of the rationals. So we're not taking, alpha isn't a set of real numbers, it's a union of a bunch of real numbers, which means it's a union of a bunch of rationals. So clearly that means alpha is a subset of Q. Let's see. E is not empty. So let epsilon be in E. So epsilon is in R is not empty either. And alpha is a union of a bunch of things, including epsilon, so alpha contains E is not empty. So alpha is a non-empty set of rationals. We're trying to show alpha is a real number, which means we're trying to show it's a Dedekind cut. So we're going through our Dedekind cut axioms. So let's let gamma be an upper bound. For E. That means if epsilon is in E, then epsilon is a subset of gamma. So if you just union all of the epsilons up, that means alpha is also a subset of gamma, which gamma is an upper bound, is a real number, so gamma is a proper subset of Q, so that means alpha cannot equal Q either. So our alpha is a non-empty proper subset of the real numbers. Cool. All right, now we need to check those slightly more complicated axioms of Dedekind cuts. So first off, let's let B be an alpha, meaning B is a rational number. So then one thing we can conclude, then B is in epsilon for some epsilon in E, because alpha is just, the union is just everything that's in those epsilons. And so first off, if A is in Q, A less than B, then A is in epsilon, so A is in alpha, and there is a C in Q with C bigger than B, and C is in epsilon, is a subset of alpha. So we see alpha satisfies our last two complicated axioms of Dedekind cuts and inherits that from all the epsilons in E. So alpha is a Dedekind cut. All right, and and alpha, of course, is our candidate for the supremum. Alpha is a superset of epsilon, which, remember how we defined ordering of the real numbers. Alpha is greater than or equal to epsilon for any epsilon in E. So alpha is an upper bound. And if beta is an upper bound, then that means beta is a superset of epsilon. Beta is greater than or equal to epsilon, so beta is a superset of epsilon for all epsilon in E. Thus, if beta contains all the epsilons, it contains their union, which is just alpha, and containment means greater than or equal to. So alpha is the least upper bound of E, and in particular, it exists. In this video, we want to clear up two leftover topics about real numbers, the last of section 1.2, and then in lecture 6, we'll move on to section 1.3. So the first thing we want to do is define the absolute value. We let alpha be a real number, and then the absolute value of alpha is, well, you all know what it is, but I'll just write it out. It's alpha if alpha is greater than or equal to 0, and it's minus alpha if alpha is less than 0. Suppose I could make this one a less than or equals to sign if you want. And then there is a straightforward proposition. Proposition 1.2.27. You let if alpha and beta are two real numbers. So first proposition, and parts 1 through C for this, by the way, are in exercise. The absolute value of minus alpha is the same thing as the absolute value of alpha. Second one is that if you take alpha and beta and multiply them and take the absolute value, that's the same as taking the absolute value of alpha and then the absolute value of beta and then multiplying them. That's just a little bit of annoying case analysis. Property C is called the triangle inequality. That's also case analysis too. You have to think about if alpha is positive, if beta is positive, if alpha is negative, if beta is negative. There's 4 cases, but the absolute value of the sum is not equal to, but it's at most the sum of the absolute values. And part D, which I will actually tell you, is sometimes called the reverse triangle inequality. The difference of the absolute values is less than the absolute value of the differences. And one other one that's obvious, but let's go ahead and write it out. Absolute value of alpha is greater than or equal to 0. And here is the proof of part D. The absolute value of A, that's the absolute value of alpha, is the absolute value of alpha minus beta plus beta. And that's at most the absolute value of alpha minus beta plus the absolute value of beta. And that is true by part C, which, as I said, was an exercise. So, alpha minus beta less than or equal to absolute value of alpha minus beta. Similarly, beta minus alpha is less than or equal to absolute value of beta minus alpha, which is equal to alpha minus beta, and that is by part A. And since the absolute value of a number, it's either that number or the negative of that number. And both of the things in this set are bounded above by alpha minus beta. We have our reverse triangle inequality. Last thing I want to state from this section is theorem 1.2.28 in your book. So this has 2 parts. The first part is that if alpha and beta are real numbers that are not rational numbers, then there is a rational number with alpha, which is between them. Notice it can't equal either of them because C is rational and alpha and beta aren't. And conversely, if A and B are rational numbers, I suppose I do have to specify the order of them. then there is an irrational number that is between them. So this is sometimes called the density property. It just says between any pair of rationals is an irrational, between any pair of irrationals is a rational. So the rationals and the irrationals, they are both, the technical term is dense in the reals. Notice here we're going to be a little sloppy about the distinction between a rational number and the real number that's the Dedekind cut of all the rational numbers less than that rational number, which we identify with that rational number. So if alpha is less than beta, then alpha is a proper subset of beta, and then you just let C be in beta but not in alpha. There must be such a C, because alpha is not all of beta. C is a rational number by construction. And then you identify C with the proper Dedekind cut. And then I'm not going to go through all the axioms. C is a subset of beta because C the real number is a subset of beta because C the rational number is in beta, so every rational less than C is in beta. And we saw before that if a rational number isn't in a Dedekind cut, in particular if C is not in alpha, then C is bigger than all the elements of alpha. So alpha is also a subset of C, the real number, because all the elements of alpha are less than C, the rational number. So alpha less than or equal to C, less than or equal to beta. And now let's move on to the next part. We should know, as I said before, these are strict inequalities because C is rational and alpha and beta are not. All right. For the second part, let T be an irrational number that's between 0 and 1. So, for example, you could take T to be 1/2 of the square root of 2, and then T is clearly greater than 0. T squared is 1/2 is less than 1 squared. So T is less than 1 by 1.2.8. All right. And we're going to let gamma be A plus T times B minus A. And then it is not too hard to check that gamma is both irrational and between A and B. We can also write this as B minus and then 1 minus T times B minus A. And it's pretty easy. And this part is positive, this part is negative. So gamma is between A and B, and if gamma was rational, then T, which is equal to gamma minus A over B minus A. So if gamma is rational, then T is rational, which it is not, which is a contradiction. So gamma is a real number, but it's not a rational number, and A is less than gamma is less than B. And that completes the proof of that.